Hello, this is Lesson 5 of the lecture series Applied Statistics Using Programming. And today we're going to talk about discrete probability distributions. So let's get started. Okay, so first, loading data into R. The most flexible function to do this is called read.table. And I copied this example from the help menu in R, and it shows you that there's so many arguments for this function. The reason that there's a lot of arguments for this function is that any data file that you get could be in a different format. You might have a CSV file, you might want to copy and paste it directly from Excel, you might want to load your Excel file directly. The formatting of the data inside the file also might be different. For example, you might have a header that has the column names, or you might have one column that includes all of the row names. You might have special characters used that might cause a problem because those special characters are used for something else in R. Some data files also have many lines in the beginning explaining what the data is or give an update, and you might want to skip those lines before reading the file into R. In other words, there's a lot of reasons why you might need to customize how the data file is being loaded into R. So this function read.table can become very complicated because depending on your usage or file, there are a lot of different formats that you might have to adhere to. As a result, you end up with a function with a lot of arguments that can be changed. Some of the most common arguments are header. Header false means that there is no header at the top. This just means there are no column names included in the file. If you want to change this, if there are column names in the file, simply change header equals true when you use this function, when you call the function. Another common change is the separator. SEP means what is separating the values. If you have a CSV file, then your separator is a comma because CSV stands for comma separated values. Therefore, in a CSV file, you would change the sep argument to a comma in quotation marks because the comma is separating the values. If you're copying from an Excel spreadsheet, for example, Excel uses a tab to delineate different values. So you would change your sep argument to a \T, indicating that it's a tab that's separating the values. So I won't go through all of the arguments here, but I want you to understand if you are having trouble loading data into R, probably one of the problems might be that maybe one of your arguments is misaligned with the format of the data that you're trying to load. A simple way to use this argument is to use the read.table, and then to load the data itself, use file.choose. This function will open a menu so that you can select the folder and eventually select the file that holds the data that you want to load into R. A different way is to simply include the full file path of the file that you want to load into R. So for example, here we have the file path on my computer followed by the name of the file, worms, and the file extension .txt because this was a text file. Always remember that you need to include your file name and the extension, which might be a .txt or a .csv or a .xlsx if you're dealing with an Excel file. If you're using a Windows PC instead, your file path may look more like this, which drive you have. Typically, it might be the C drive, and where on that computer is your file path. Finally, at the end, we have the name of the file again, and the extension, the file extension. You can find the file extension by right-clicking the file and going to Properties, and it should list what type of file you're dealing with. So TXT file is not a very common way to store data. Instead, a CSV file is much more common. A CSV file stands for comma-separated values. And what it is a file that literally has only the values that you want separated by a comma. The comma is telling R, or whichever program that you're using, that before the comma and after the comma are different columns. Okay, so the benefit of using a CSV file is that there's no formatting information involved. For example, if you save an Excel file, there's a lot of formatting information that needs to be saved with your file. For example, if you highlighted text and turn it red, or bold some words, or perhaps change the font, all of this formatting information needs to be saved somewhere in the file. What ends up happening is if you have a large data file and also have to include all of that formatting information as well, your file becomes too big. So a lot of big data files are saved as a CSV file because no formatting information is saved with the values. It's only the values that are being saved. This is very useful if you're opening your file using Python or R, because R and Python don't need all that extra formatting information. Instead, they only need the values themselves. There is a separate function called read.csv because CSV files are used so often. It's very similar to read.table, but it sets the separator as a comma for obvious reasons, and it sets the header as true because this is the most common data type typically used in R. Copy and pasting can be an easy way to transfer data from an Excel file into R. The way that you can do it, if you're on Windows, is to use Clipboard. Before running this code, you would highlight your data that you want to copy, press Control-C or copy, and then enter the code in R. If you did it correctly and you enter your code like this, it should load your data successfully into R, and then you can use that data as a data frame as whatever object you saved it as. One of the problems with R is that there is no built-in function to load an Excel file. Luckily, that's not a problem. We just need to do a little bit of preparation. How? We can install a package that allows us to use Excel data in R. So first we install the package. So we download it from the internet to our computer. Then we load it from our computer into the R session using a different function called library. So the library OpenXLSX allows us to load Excel files directly from the Excel file into R. First, we need to install the package using install.packages and our package name. Then, to use the function in R, we use library OpenXLSX, and then we can use the function read.xlsx. Before using this function, we need to first install the package. If the package was installed successfully, then we can use this function here. Because Excel files have multiple sheets, we may also have to identify which sheet in the Excel file we want to load into R. So we have the extra argument sheet, and then you can include the sheet name if you're dealing with an Excel file with multiple sheets. Again, the location of the file is the same. We find which folder the file is located in using backslashes. Then we have our file name and the file extension. The file extension for any modern Excel file is currently XLSX, indicating that you have an Excel file. So one thing that's really useful is to set your working directory. The working directory is the file path In other words, the folder on your computer where you're holding any data files that you want to load into R. It is where any files are loaded in or exported out. So you can set your working directory, and then you don't need to input the file path every time you load a file. Instead, to load the file, you can just use the file name and extension, and you don't need the file path because your working directory is telling R where that working directory is. If you want to know where it is, we don't need to set it. We can also say get working directory, and that will tell us where we're saving things. So currently, this is the folder that R is checking to find any files or anything that I'm saving or exporting from R. If you want to change that, you can use the set working directory and set a new file path to which folder you want to load or save data to. So there are several ways that we can load data. Let's try to load a data file into R using the File Choose option. File Choose will open a window selector where we can find which file we want to load. I want to load the file called airline-data.txt. So I'm going to hit open. And what it did was it opened this file. Let's check our console to see the results. This is the file that it opened, but my data looks all messy. Actually, it didn't load the file correctly. The reason is I need to set some extra parameters. So in this case, some of the parameters that I need to set are the separator of the file that I'm going to use is separated by a comma. So let's try this. Let's choose the same data. And let's say open. All right, now my data looks cleaner. I think everything worked. So let's look at the top of my data. Here are my column names, V1, meaning variable 1, V2. These are the default column names if there's no column names. Then my first line of data, 1, is my first row. I see obs, FLT. These are actually the column names. And then my data starts after that. So in other words, the data was loaded incorrectly. Why? Because the first row is actually the column names. So I should identify that if these are the column names, then it means we need to tell R that we have column names, so it should read them when it loads the file. So let's try one last time. We're going to use file choose, but we have to add the arguments separator equals a comma and header equals true. Let's try again. Here's our file, open it. Let's check those column names, and now we see the column names are correctly the column names that they should be, and our first row of data looks like data. Great. So in most cases, even though you know where your file is, you might include your file path, your file name, your file extension, but you need to adjust the other arguments of your read table command in order to read the data format that is formatted in that specific file. Here are some other examples. So if you have a header, we would add that header equals true argument. If you have separators or a comma, you would add that separator equals a comma argument. If you're using this line of code here, because you're using a CSV file with a header, we can simply use the read.csv function instead, then we can only give the file name. Why? Because by default, the read CSV function uses a separator as a comma and uses a header is true. The last example is finding our data and using a clipboard. Since I'm using the Mac version, let's try to run this code. So first, I need to open my file. Let's open this Excel file. The file opens in Excel, and now what I'm going to do is highlight all the data that I want to include. Okay, so now that I have all the data that I want to include, I'm going to Control C or Command C to copy it. You can see the dotted line shows up. And immediately after, I'm going to go to my code and just run my code. Now let's see if that worked. Now let's check our data. And it looks like our data loaded correctly. Okay, so this pipe PB paste is used on a Mac because there's a little bit of a different functioning of how the clipboard works. However, if you're on Windows, you can simply write clipboard in quotation marks and it works the same way. Now there's one thing that we need to remember. If we're copy and pasting from an Excel file, we should include this separator equals \t. What does this mean? This means that a tab is used to separate each cell of our Excel file. It's how Excel saves the file data. If I want to load the Excel file directly, I can simply use this function openxlsx, select the closest server to me, and this downloads your package from the internet to your computer. Next, we want to load the functions from that package into R. We can use the library function to do this. Finally, let's use that readxlsx function, which is located inside the openxlsx package. Now, what is the file path and file name? If this is the data that I want to copy, I can right-click it, and on Mac, I can hold down the Option key, and you'll see that some of my options change. One of those options is copy file name as a path name. Click that, go back to R. I'm going to paste. What that did is it took my entire file path and my file name and extension and put them onto my clipboard. In this case, I don't have any sheets. I only have that one sheet. So I'm just going to run this xlsx function, see if that worked. And we can see that that loaded directly from an Excel file, an xlsx file. And it's good practice just to check that file and make sure that everything loaded as you might expect it to load. So now that we know how to load our own data if needed, let's talk about discrete probability distributions. We're going to cover a few of them today: uniform distribution, binomial distribution, and the Poisson hypergeometric distribution and geometric distribution we'll just explain in less detail. So let's get started. What is a discrete probability distribution? To understand a discrete probability distribution, we need to understand what a random variable is. A random variable is a function or rule that assigns a numerical value to each outcome in the sample space of a random experiment. The nomenclature, to explain it, we use uppercase letters to represent random variables. So anytime you see a capital X or a capital Y, that means we're dealing with a random variable in statistics. Lowercase letters represent values of the random variable. A discrete random variable has a countable number of distinct values. So a discrete random variable is different from a, let's say, continuous random variable. Let's explain a continuous variable very briefly. So if I said, how many numbers are between 0 and 1, what is the answer? Well, you might say one number. Well, there's 0 and there's 1. Maybe that's two numbers. Well, what about 0.5? Well, that's a number. What if I said 0.51 or 0.511 or 0.511111? We can continue to do this infinitely. In other words, there's an infinite set of numbers between 0 and 1. This means that it's very difficult to calculate the distribution using a discrete probability distribution. Discrete means we can count the numbers or the possibilities. A discrete probability distribution means that our sample space is not infinite. Okay, so that's why we say that a discrete random variable has a countable number of distinct values. So, a discrete probability distribution assigns a probability to each value of that discrete random variable x. To be a valid probability distribution, the following must be satisfied. If x has n distinct values, x1, x2, blah, 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 until xn, the total number of values you have, then the probability of x is between 0 and 1. Could be equal to 0 and 1, but it's between or equal to 0 and 1. The sum of all of those probabilities equals to 1, or 100%. All right, so let's look at an example. Rolling a die. A die is one dice. Okay, so if we roll a die, we have a discrete probability of rolling any specific number. All this means is we can count the possible values that we can end up with. We can end up with a 1, a 2, a 3, a 4, a 5, or a 6. Okay, so it's discrete because we can count exactly what are the possible outcomes. Our sample space, shown on the left, is the range of possible values of a random variable. In other words, this sample space is what are the possible values that we can possibly get. Our random variable x is initially unknown number, which is different each time an event, trial, or experiment occurs. Every time we roll that die, it can be a different outcome. In other words, it's random before we roll the die. It's unknown until we observe the outcome. A probability distribution assigns a probability to each outcome, to each value of a discrete random variable x. In this case, our random variable is just a single die. Let's say we are flipping a coin. We flip a coin 3 times. What are the possibilities? What is our sample space? Our sample space is all of the possible outcomes that we can get when we flip a coin 3 times in this example. So we could get heads, heads, heads. We could get heads, heads, tails, heads, tails, heads, tails, heads, heads, right? This is the total possibility of all of the outcomes that we can get. So if x is the number of heads, then x is a random variable with the following probability distribution. If we look over here, here is our probability distribution of the number of heads. We could get 0 heads, meaning we got tails 3 times, right? So x would be 0 because there's 0 heads. There's a 1 in 8 chance. What is the 8? 8 is the total possible outcomes that we can have. If you remember the Monty Hall problem that we discussed in the first video, that is exactly how we solve that problem. We look at the total sample space, and then we calculate what is the probability from that sample space. What is the probability of 1 heads? 3 out of 8. What is the probability of 2 heads? 3 out of 8. What is the probability of getting all 3 heads? 1 out of 8. Outcomes would give you that. A probability distribution function, what we see on the left, is a mathematical function that shows the probability of each x value. On the left, we see a PDF. A PDF is a probability distribution function. It's a mathematical function that shows the probability of each x value. So in this example, the highest probability is to get the value 7. And that occurs about a little bit more than 20% of the time. This probability distribution function is showing you the probability of each specific value in our sample space that x could hold. On the y-axis, we have the probability of that occurring, and on the x-axis, we have the value of x across the entire sample space. So, as we mentioned previously, if we add up the probabilities of everything in our sample space, we get 100%. So that lets us create a cumulative distribution function, a CDF. That's what we see on the right. A CDF is a mathematical function that shows the cumulative sum of probabilities, adding from the smallest to largest x value, gradually approaching 100%. If we add all up until 10, we have about 95%. If we add up all the numbers up until the last value in our sample space, we get 100%. So that's what this CDF curve is mapping. Let's talk about expected value. Expected value is the sum of all x values weighted by their respective probabilities that represents a measure of central tendency. Because each x value in your sample space has a different probability, if we weight the x value with the expected probabilities, then we'll get what we can use as a measure of central tendency. If there are n distinct values of x, then our central tendency, mu, can be calculated as x, or each value, times the probability of that value occurring. The expected value equals mu. Mu is the average. In this case, we're looking at a weighted probability. So we have xi times the probability of xi, the sum over the entire sample. What does this mean? It means each value is multiplied by the respective probability of that value occurring. And then we do that and add them all together, and then we end up with our expected value. This can tell us the average when probabilities are involved. So let me give you an example. Let's say that you have an Airbnb and you have multiple rooms in your Airbnb. Let's say you have a total number of 4 rooms. So our sample space is 0 rooms might be reserved. Nobody reserved a room. Maybe 1 person reserved a room, or maybe all 4 of your rooms are reserved during a specific weekend. Okay, well, what is the probability of x? In general, we might look at historical data. Let's say, for example, you own the Airbnb. You might look at your records and say, over the past 10 years, we can calculate the probability of how many people are reserving the room during a given weekend, right? You can look at some sort of past data and make an estimate of what these probabilities are. This is how it's usually done in practice. Okay, so let's say we have, if I want to know what is the average number of rooms, what is the average number of rooms reserved? Well, we can use the probabilities and multiply the probabilities by the rooms reserved to come up with a number that represents a central tendency, how many I might expect on any given weekend. So in this case, if this is my sample space, and these are my probabilities, and these are my probabilities for each one of those occurring, I would end up with this equation. Just multiplying every x value times the probability of that x value occurring and summing them together, just adding them together, and that gives us our average or expected value over these probabilities. All right, so how about variance? How can we calculate the variance of something like this where we have a sample space and a different probability for each one occurring? Variance of a discrete random variable is weighted by the probabilities, so it is a weighted average of the dispersion about the mean. So the standard deviation is just the square root of the variance again. All right, so here is our variance formula, and what we see is x minus mu. What is mu? That is our expected value. X is each value of x. Then we square it and multiply it by our probability of x. And this is how we can change our variance formula to accommodate for probabilities in a sample space. So what is our variance? About 1 room is our variance. What does that mean? It means on average, we should have about 1.5 rooms reserved every weekend, plus or minus 1 room. Some weekends are a little bit more busy, some weekends are a little bit less busy. We might expect generally, on average, plus or minus 1 room. All right, so let's look at how to calculate expected value using R. In this case, my random variable x has the sample space 0, 1, 2, 3, or 4. These are the rooms that can be reserved. Next, I have different probabilities for each one of these observations occurring. In other words, the probability of having 0 rooms reserved is about 18%. Having 1 room reserved is 34%. Having 2 rooms reserved is 35%. 3 rooms is 11%. And all 4 rooms is 2%. So we'll load those as the probability of x. Then we can look at that result in a data frame. Here's our x, here's our probability of x. All right, so if I take x and I multiply it by the probability of x, I get a vector of the x times probability of x, right? So this is 0 rooms times 18%. This is 1 room times 34%. This is 2 rooms times 35%, and so on. If I add those all together, I get mu, or my expected value. Let's look at our weighted mean function. This weighted mean function can do the same thing. We just have to input a vector of x and a vector of the probability of x, and that will calculate mu for us using this weighted mean function instead. We'll get the same result doing either one. Next, expected variance. Using the formula shown in the presentation slides, we can calculate it as follows. Here's our variance, and here is our standard deviation. Okay, that's how we can use our expected variance and expected standard deviation given a set of discrete outcomes, x, and a set of probabilities of those outcomes occurring, probability of x. All right, so let's look at specific discrete distributions. The first is the uniform distribution. The uniform distribution just means everything has the same probability. So, what are the characteristics? The discrete uniform distribution describes a random variable with a finite number of integer values from a to b, the only 2 parameters. What does that mean? Well, it means that we have a discrete number of outcomes, and those outcomes range from A to B. Okay, so in order to calculate our distribution, we have 2 parameters. We need to know the A value, the minimum, and the B value, the maximum. And if we have that information, we can calculate everything else because everything has the same probability. So each value of the random variable is equally likely to occur. I find these as very useful. Up here we have the mathematical formulas. Up here we have the parameters of this distribution, the PDF formulation, the CDF formulation, and if we look down here, it gives us the mean, how to calculate the average, and how to calculate the standard deviation in this distribution. Right down at the bottom, we get an Excel formula to calculate this. Now, if you have experience in Excel, it might be fun to write this formula and check the difference between this result and your R result. They should be the same. To get probabilities from a PDF function for specific value of x in x, random variable x, in other words, to get each value of x, so in the sample space, the possible outcomes in our random variable x, we can use the function ddunif. And here's how it works. X is our data, min is the minimum of our data, max is the maximum of our data. To use this function, we need to use this extra distribution package. Some distributions are already loaded into R. Others, like the discrete uniform distribution, is not already there, so we need to use a package to use it. So here's our function where x is the specific value of x. This probability where our random variable equals the specific value of x for a uniform discrete distribution. Get cumulative probabilities from CDF function for a specific value of x in x. So instead of using DD unif, we use PD unif, meaning the probability of a discrete uniform function. Again, we need the value of x that we're checking, the minimum and the maximum. We can sample from a uniform discrete distribution using the sample function that we looked at in a previous video. The sample function works like this. We say x, n, and replace equals true means we can select the same value more than once. An example of the uniform distribution is rolling a die, as we described earlier. Every number between 1 and 6 are equally likely when you roll a die, right? The probability of getting any of these on a roll of a die will be 1 of 6 because there are 6 possibilities and we're going to roll only one of those 6 possibilities. So quite simply, it's 1 of 6. Pretty easy. So below on the left, we have the PDF. The PDF shows the probability of each outcome of x, and we can see that they're all the same. Why? Because it is a uniform, meaning the same probability for all of those discrete outcomes. If we look at a CDF, we see that the CDF, the cumulative distribution function, is a linear relationship because we're just adding all the previous probabilities together. What is the average value when you roll a die? Well, you should expect to roll a 3.5, right? What does that mean to roll a 3.5? It means this is the expected value. It doesn't mean that it can actually occur. It's just telling you that based on the numbers that we have, 1 to 6, and all of them have the same probability, the average of that being equally weighted is 3.5. The standard deviation is 1.7, meaning we expect you'll probably get a 3.5 or plus or minus 1.7. Next, let's look at the uniform discrete distribution in R. As mentioned, we need to install the package extra distributions, and then we can use it. So DDUNF means the discrete probability in a uniform distribution. So what we see is the values 1 to 6, we have the same probability for each outcome, 0.16666 repeating for every outcome of our die roll. If we made a bar plot, we can make our PDF using a bar plot function. And it's not very complicated. On the bottom, on the x-axis, we have each possible value of x occurring, and on the y-axis, we have the probability of that occurring. This is our PDF. To calculate the probabilities in a CDF, we can use the following function, the PDUnif function. And that gives us the probability of 1 occurring, the probability of 2 or less occurring, the probability of 3 or less occurring, the probability of 4 or less occurring, the probability of 5 or less occurring, the probability of 6 or less occurring. In other words, this last probability is the probability of 6, the maximum number, or a lower value, which is 1, 2, 3, 4, 5 occurring, is 100%. 100% of the time, you're going to get a value of 6 or less. So if we wanted to plot in a bar plot, we can do that as follows. So this is what our result looks like. It looks very similar to what it shows in the lecture slides. To find the mean and standard deviation of our dice roll, again, we set x as the sample space, and probability of x is the probability of each one of those occurring. We can use our weighted mean. We can use our sum function as follows. And so this tells us that we should expect to roll a 3.5, just as it says in our lecture slides. To understand a binomial distribution, we should first understand a Bernoulli experiment. It's a random experiment with only two outcomes. One outcome is arbitrarily labeled a success. It doesn't matter which outcome it is. We just say one of the outcomes is a success. We say the success is x equals 1, and the other one is a failure. We say that one is x equals 0. So 0 is a failure, 1 is a success. It doesn't mean they're good or bad. We're just labeling the two outcomes. Either it's a success or a failure of whatever we labeled arbitrarily. Pi, not 3.14, but pi, the symbol, is used to denote the probability of success. 1 minus pi is obviously the probability of failure. If you're not successful, then you are failing. The probability of success remains the same for each trial. Every time we do the experiment, the probability of success before doing the experiment is always the same. Note that the probability of 0 and the probability of 1 is equal to 1 minus pi plus pi. So in total, this equals 1. Either the probability of success plus the probability of a non-success, the probability of a failure. These are the two options, and as we know, the total probability must equal 100%. So the probability of a failure and the probability of a success equals 1. Each probability has to be between 0 and 1, or it could be equal to either one. The expected value and the variance of a Bernoulli experiment can be calculated as follows. So a binomial distribution is what we end up with if we have a Bernoulli experiment repeated. In other words, if every time we do something, we have some probability of success and some probability of failure, and we do that thing more than once, we end up with a binomial distribution. Each trial, every time you do that thing, each trial is independent. It's not related to the other times you did it. So the probability of success, pi, remains constant on each trial. In other words, if I flip a coin and I get heads, the probability of getting heads was 50%. The probability of failing to get heads is also 50%. Every time I flip that coin, it doesn't matter what the previous result was. Every time I flip that coin, the probability is the same. It's always 50%. Even if I got tails 100 times in a row, the next time I flip that coin, it should be the same probability of 50%. In a binomial experiment, we're interested in x, the number of successes in n trials, how many times you tried it. So x equals x1 plus x2 plus blah, 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 xn. These are the outcomes of your trials. The probability of a particular number of successes, probability of x, is determined by the parameters n and pi. What is n? N is how many times you do it. What is pi? Pi is the probability of success. So how many parameters do we have in the binomial distribution? We have 2. We need to know how many number of trials there are, how many times we tried it. What is the probability of success each time you tried to do that thing? All right, so to get probabilities from a PDF function, we can use the d-binome distribution. And x is the number of successes, size is the number of trials, and probability is the probability of success on each one of those trials, pi, right? To get the cumulative distribution function, to get the CDF, we can use the function p-binome. Q is the vector of quantiles, all the values from the minimum to q. Size is the number of trials, and probability is the probability of success, pi. Here's an example. Let's say guests to your inn or your Airbnb will be early or not. So it's a success if they're early, it's a failure if they're not early, okay? It doesn't mean that one is better than the other. It just means that we're just arbitrarily labeling if they're early as a success. On average, let's say 20% of guests at my guest house are checking in early. Today, 4 guests are expected to check in today. What is the probability that 1 out of the 4 will check in early? How can we define this example? X is the number of early guests. We either have 0 early guests, 1 early guest, 2 early guests. In this case, I'm checking what is the probability of 1 early guest. The probability of them arriving early is labeled as pi, which is 20%. So the failure rate, or the 1 minus pi, is 80%. The range of x, the possible values are 0, 1, 2, 3, or 4. So let's quickly take a look in R at how to do this. Next, let's look at our binomial distribution. All right, we have x equals 0 to 4. These are the possible values of the total number of rooms that I might have. Then I have pi, which is the probability of success, meaning the probability of a guest being early, which is 20%. And the number of trials, or the number of total trials, is 4, because there's 4 rooms. So, in other words, the probability of a guest being early is 20%. I have 4 rooms, so that means there are 4 chances of a guest being early. So, using the d-binom function, we can input x, which is every value of our vector, 0, 1, 2, 3, 4. What is the probability of 0 guests being early? It is about 41%. What is the probability of 1 guest being early? It's about 41%. What's the probability of 2 guests being early? About 15%. What is the probability of 3 being early? Only about 3%. If I were managing a business, I might prepare for up to 2 guests to be early, and it's much less likely that 3 or 4 guests are going to be early. So that might mean that when I'm making decisions, I might need to make sure that I have 3 rooms that are available early, but it's much less likely that all rooms will arrive early. Let's look at our CDF. The probability of 0 rooms being early is about 41. The probability of 0 or 1 rooms being early is 81%. The probability of 0, 1, or 2 rooms is 97, and so on. We can also use the inverse of the CDF function. So what is the probability of, in a class of 13 people, what is the probability of at least 1 person's birthday today? Well, what is the probability of any specific person's birthday? Let's say it's 1 out of 365. I know you have leap years and it's not exactly 1 out of 365, but let's keep things simple. So the probability of someone's birthday, of a specific person's birthday, is 1 out of 365. If there's 13 people in the class, then n is 13, and these are the number of possible birthdays. There could be 0, or there could be up to 13 birthdays, because there's 13 people in class. All right, so to calculate the probability of at least 1 birthday, we could calculate it 1 minus the p-binom, the cumulative distribution, as such. Okay, so what is that? 0.03, so about 3.5%. Okay. Alternatively, we can use this function. Instead, this will calculate the same amount because we said the lower tail is false. So either, if we want to use an inverse CDF, we can say 1 minus p-binom, or we can use our CDF function, but we can say lower tail equals false, meaning we're looking at the upper tail. We're doing it inverted. Okay. Okay, so what is the probability? We can print it as follows. Some other useful discrete distributions are the Poisson distribution, the hypergeometric distribution, and the geometric distribution. The Poisson distribution describes the number of occurrences within a randomly chosen unit of time, a minute, an hour, or a space, for example, a square meter, a kilometer, a mile. So here's an example of what would follow a Poisson distribution. The probability of a specific number of customers that will arrive at the lobby per hour. This is useful for managing how many people are needed for staffing, for example. A hypergeometric distribution is similar to the binomial distribution, but unlike the binomial, sampling is without replacement from a finite population of n items. A finite population n containing a known number of successes, and sampling without replacement, n items in the sample, where the probability of success is not constant for each sample item drawn. Let's look at an example. 1,000 tourists are allowed to enter a destination every day. On average, 10% of tourists are not satisfied with the destination. If you sample 10 tourists at the destination, what is the probability of all 10 being unsatisfied? This is an example that you can solve using a hypergeometric distribution. The geometric distribution describes the number of Bernoulli trials until the first success. So here's an example. How many tourists need to be sampled until we find one that is unsatisfied with the destination? I think these make it a little bit more clear how these other discrete distributions might be used. Okay, so we mentioned a few other discrete distributions here. So one of those is the Poisson distribution. So based on the last year of data, on average, 20 guests arrive to the hotel lobby per hour. All right, so lambda in our Poisson distribution, lambda is defined as the average number of events per time period. In this case, we're setting the time period as per hour, and based on some data, we say that on average 20 guests arrive per hour. Okay, so that is how we distinguish lambda, and lambda is the only parameter for the Poisson distribution that we need to define. Okay, so what is the probability that exactly 30 guests will arrive in the next hour? Well, let's say, for example, you have a hotel lobby and guests are always coming in, and on average, 20 people come in. And you can only have up to 30 guests in that room. Okay, well, what is the probability of exactly 30 guests arriving in that hour? We have 0.008. But what is the probability of 30 or more guests arriving? In this case, this is to calculate the probability of more than 30 arriving, which is 0.01, about 1%, a little bit more than 1%. We can also use this function here to do the same thing as this 1 minus. Okay? All right, so that is the Poisson distribution. Here's our example with the hypergeometric distribution. So as we said, 1,000 tourists are allowed to enter a destination every day. On average, 10% of tourists are not satisfied with the destination. Let's say we sample 10 tourists. What is the probability that all 10 are unsatisfied? We're sampling 10 tourists, so our sample space is 10, 0 to 10. M is the number of tourists who are unsatisfied. So that is 1,000 times our percentage. So that's about 100 tourists in general. The number of tourists satisfied are 90% of those tourists. And K is the number that we're sampling. So we know how many are unsatisfied. We know how many are satisfied. And if we take a sample of our population, what is the probability that all of them are unsatisfied? In other words, all 10 are going to be unsatisfied. We get 6.5, error minus 11. In other words, that means 6 with 10 zeros before it. So that's 0.0000000006. Okay, that's a really small probability that everybody in our sample of 10 people will be unsatisfied. Let's make a bar plot to see what is the probability of drawing each one. So the probability of all 10 is almost 0. It's just a really, really small number. So what is the probability that 0 in our sample of 10 is unsatisfied? Actually, it's quite high. So if I took a sample of 10 people and said nobody is unsatisfied, I would be incorrect, because this can happen very often, even if a large number of people are unsatisfied with the destination, right? So this tells you the probability of any specific value occurring. Cool, pretty cool. All right, so let's try to solve this geometric distribution problem. Using the same example from the above distribution, how many tourists need to be sampled until we find one that is unsatisfied with the destination? Now, here is our code, and it can be a little bit confusing because we start with a 0. Now, let's look at our result. If we look at our result, we see that the probability is 0.1. So in other words, 0 gives us 10%. And to understand why that is, we need to check the distribution. And what it says is, let's make it a little bigger. We input the value, and it represents the number of failures in a sequence before success occurs. So if we have 0 failures, that means that's the number of successes occurring the first time. In other words, if 0 failures occur, that means that the first time was a success. So that's why we include 0 here, which is a little bit unintuitive, I think. Okay, so let's see our PDF distribution. So this is showing us the probability of getting a success after sampling X number of tourists. All right, so this has been lesson 5 in the series Applied Statistics Using Programming. I'm Dr. Ian, thanks for watching. Hopefully I'll see you in the next video when we talk about continuous distributions. Thank you. So every time we do the experiment, the success, the probability of to be valid, it must follow this. What? To get cumulative. Thank you. Thank you. Thank you. All right, one of those will work.